Hello friends, welcome to engineering tutorial. So in today's video we are going to discuss another important concept related to the subject of control systems, and today's topic of discussion is time response analysis. Okay, so what is time response analysis? So we know that in control system or any system, any system, we give some input to it. We give some input and we get some output. Now, in the subject of control systems, the input or it is generally taken in the time domain, time varying input, and the output also is time varying. So this variation of the output of the system with respect to time is called as time response of the system. And the analysis, the study of the output with respect to time is called as time response analysis. Now we know that in control systems analysis, Laplace domain approach is used, or S domain approach is used. So it is converted into S domain, it is RS, and this becomes CS. CS and RS. So the Laplace transform of any time varying function, the Laplace transform of any time varying function, let's say ft, is given by one-sided Laplace transform I am talking about. It is 0 to phi, integration from 0 to phi ft e to the power minus st dt. This is the Laplace transform. Where S is a complex parameter given by S j omega, where omega is the angular frequency. Now I have already discussed about the basic concepts related to systems, transfer functions, open loop transfer functions and closed loop transfer functions, so you please check out those videos. So the study of the output of the system is time response analysis. Now why it is important? Suppose we have an unknown system, we have an unknown system, we do not know its features, we do not know its characteristics. So how to evaluate it? So in order to evaluate, in order to understand an unknown system, time response analysis is used. So how it is analyzed? So what is done is that to the unknown system, to the unknown system, some known input, known input signals are given, whose characteristics are known. The characteristics of the input signals are known. Those input signals are given to this unknown system, and from the nature of the output of the unknown system, from the nature of variation of the output of the system, this unknown system with respect to time, the characteristics of the system is determined. So if you want to have a proper definition of time response analysis, it is the analysis of unknown systems by application of some known input signals and studying the nature of output variation of the system with respect to time. Okay, so the study of the nature of variation of the output of an unknown system with respect to time upon the application of some known input signals is called as time response analysis. So the known input signals that are generally given to this for the analysis of these unknown systems, they are generally step function, okay, step signal or a step function, a ramp signal, or it's called as ramp function, parabolic signal or parabolic function it is also called as, or a impulse function. Okay, impulse function. These signals are commonly fed as input to this unknown system, and from the response that this system gives due to these input signal functions, by studying that response, by studying the nature of variation of the output with respect to time, the characteristics of this unknown system is determined. Okay, so I have already discussed about step function, ramp function, parabolic function and impulse function in the signals and system section, okay, where I have posted many videos related to these signal functions. Apart from that, from other signal functions, I have also posted videos related to that, both in continuous time domain and discrete time domain analysis. So you please check out those videos before going into this video. So by the application of these known input signals whose characteristics are known, we know the characteristic features of step function, we know the characteristic features of ramp function, we know the characteristic features of parabolic function, and we know the characteristic features of impulse function. So by these the application of these known input signals to this unknown system, the nature of the output of these unknown system is determined, it is studied, and that is called as time response analysis, which helps in determining the characteristics of these unknown system. This is called as time response analysis, and this chapter, this topic will revolve around this only. Okay, now we have already discussed about the basic signal functions in the signals and systems portion, but still let us just have a quick look at all the signal functions that will come across in time response analysis, which will be used in the analysis of the unknown systems, just to have a clear understanding. So first signal function is the step function. So the step function, it is represented in this way, okay, the variation with respect to time, and this is the output. So the step function, it looks something like this. It has a constant magnitude, okay, let's call it A. Okay, the step function is called as ut. Okay, so if this value is equal to 1, if this value becomes equal to 1, it is called as unit step function. So the step function will have a constant magnitude, okay, the step function will have a constant magnitude for t greater than equal to 0, and will have a value 0 for t lesser than 0. Okay, and if this value, constant value, is equal to 1, then it becomes unit step function. Okay, so this is about step function. So in the analysis of the output of the unknown systems in the time response analysis, we have to use S domain approach or Laplace transform approach. So we have to consider the Laplace transform of both the input and the output. So here the Laplace transform of the unit step function, okay, unit step function is Laplace transform of A. Because it has a constant magnitude A, it is A by S. We can write A as A into t to the power 0. Okay, we can write it as that. So Laplace transform of A into t to the power 0 is equal to A into Laplace transform of t to the power 0, okay, which will be equal to A by S. So the formula which we are using here is Laplace transform of t to the power n is equal to n factorial by s to the power n plus 1. Okay, so that formula we are using here. So it is 0 factorial by s to the power 0 plus 1, which is equal to A by S. That concept we are using. So always remember, the Laplace transform of unit step function is equal to A by S if it is for a step function. And if it is unit step function, Laplace transform of a unit step function, if the magnitude of the value of A is equal to 1, so then it will be simply 1 by S. Okay. So the next basic function which is used in the analysis of control systems is the ramp function. Okay, the ramp function. So the ramp function, it looks something like this. Okay, so the ramp function it looks something like this. Okay, so it is represented as RT, the ramp function, is equal to AT for t greater than 0, greater than equal to 0, and 0 for t lesser than 0. This has a slope equal to A. Okay, so it is a function which increases linearly with time. Okay, so it has a slope A. Now if this slope value becomes equal to 1, it will become unit ramp function if the slope is equal to 1. So it will become unit ramp function, and it will only be RT equals to T. Okay, the unit ramp function for t greater than equal to 0 and 0 for t lesser than 0. Now again, since we have to use Laplace domain or S domain approach, so the Laplace transform of ramp function, it will be A by S square. How? It will be the Laplace transform of AT. Laplace transform of AT will be equal to A, since it is a constant, into Laplace transform of T, which will be equal to A into t to the power n. N here is equal to 1, so it will be A into 1 factorial by S to the power 1 plus 1, which is equal to A by S square. Laplace transform of t to the power n, the formula which you are using again, Laplace transform of t to the power n is equal to n factorial by S to the power n plus 1. Same. So the Laplace transform of ramp function is equal to A by S square, the Laplace transform. So always remember, the Laplace transform of ramp function is A by S square. Okay. So the next basic signal function which is used in the analysis of unknown control systems is the parabolic function. The parabolic function. Okay, so the parabolic function, it looks, the parabolic function, it looks something like a parabola. Okay, so this is the parabolic function, and it is represented as pt is equal to 1 by 2 a t square for t greater than equal to 0 and 0 for t lesser than 0. Okay, so this is the parabolic signal function. So that is not like this. Okay, yes, this is the parabolic signal function. Okay, so again, converting it into the Laplace transform domain or the S domain, the Laplace transform of the parabolic function will be Laplace transform of 1 by 2 at square, which will be equal to 1 by 2 into a. Since they are constants, they will come outside the Laplace transform of t square. So it will be a by 2 into 2 factorial by s to the power 2 plus 1, which will be a by 2 into 2 by s cube. 2 will get cancelled, so it will only be a by s cube. Okay, so the Laplace transform of parabolic function is a by s cube. Okay, so this is the Laplace transform of parabolic function. Always remember these the transforms of the various basic signal functions: the step, the ramp, the parabolic, and the next we'll discuss about the impulse function. Okay, so the next signal function which is used is the impulse function. Okay, impulse function. Okay, so it is a very special signal function, okay, in terms of its characteristics. Now the impulse function, it exists only at the time instant equal to 0, at origin. Okay, it exists at the origin and it has a value equal to unity. Okay, so the impulse function is represented as this, which is equal to 1 at t equals to 0 and 0 elsewhere. Everywhere else it is 0. So it only exists at t equals to 0 and its value is equal to unity. Okay, and another important feature is the Laplace transform of the impulse function is equal to 1. This is the unit impulse function. Okay, this is the unit impulse function since it has a value equal to unity. So this is another very important characteristic of the impulse function. So the first important characteristic is that it exists only at t equals to 0 and it has a value equal to 1, the unit impulse function, and it is 0 everywhere else, and the Laplace transform of the unit impulse function is equal to 1. Okay, so here we have discussed the basic signal functions which are used in the analysis of systems. So another important and interesting concept associated with the signal functions is the interrelationship between the various signal functions. Now, the parabolic function, it is represented as this: pt is equal to 1/2 at square. Okay, suppose we differentiate it, differentiate it with respect to time. So this will be 1/2 into a into 2t. Okay, 2 will get cancelled out, it will become at, which is nothing but the ramp function. Okay, the differentiation of parabolic function gives us the ramp function. Okay, again, this is the ramp function. RT is equal to AT. Suppose we differentiate it with respect to time. dRT by dt, it gives us A, which is nothing but the step function. Okay, step function ut. Okay, which is the step function. So from this, what we conclude, that the derivative of the unit parabolic function gives us the ramp function. The derivative of ramp function gives us the step function. Again, if we further differentiate the step function, okay, dut by dt, the constant dut by dt, the differentiation of a constant is generally equals to 0, but actually this gives us the impulse function. Dut by dt is equal to the impulse function. Why? Because the impulse function, as I said, it is a very unique signal function. It exists only at t equals to 0. Okay, so always remember this 3 important relationships. These are very important. Okay, the derivative of the parabolic function gives us the ramp function, the derivative of the ramp function gives us the step function, and the derivative of the step function gives us the impulse function. Okay, so always remember these 3 important interrelationships between the signal functions.